Why is garbage collection in Apache Cassandra so crucial, and how does it impact performance? It's a question that warrants some investigation. Garbage collection, or GC, is a fundamental part of Cassandra's memory management. However, several issues can lead to GC problems, which in turn can lead to performance degradation or even cluster instability. Let's delve into these problems and their potential solutions. Heap size misconfiguration is a common culprit. If the heap space is too small, frequent GC cycles may occur as the JVM struggles to reclaim memory. On the other hand, an overly large heap size may cause longer GC pauses, impacting cluster responsiveness and even leading to out-of-memory error exceptions. The solution lies in careful calibration, ensuring heap size is optimally configured for your specific workload. Next, consider the impact of high write throughput. Intense write workloads can create a plethora of objects in memory, increasing GC overhead. This can lead to longer GC pauses and reduced throughput. Mitigation strategies include carefully managing your write load and avoiding large batch operations or inserts that can spike memory usage. Large partition reads also pose a problem. If the data can't fit in memory and requires extensive disk I/O, this can lead to increased GC activity. To avoid this, consider strategies like reducing your partition size or limiting the scope of your scans. Long compaction tasks can also contribute to GC issues. Compaction merges S tables to improve data organization and disk space utilization, but it's a resource-intensive process. Large S table sizes or frequent compactions due to high write throughput can exacerbate the problem. To circumvent this, consider tuning your compaction strategy based on your workload characteristics. Improper data modeling practices can also lead to increased memory usage and GC pressure. For instance, creating wide partitions or using too many secondary indexes can strain memory resources. A well-designed data model, tailored to your specific use case, can help alleviate this issue. Suboptimal query patterns add to the problem. Queries generating large result sets or performing full table scans can strain memory resources. High-frequency queries with poor selectivity or inefficient filtering criteria can also lead to excessive memory allocation and GC overhead. To mitigate this, optimize your queries to be as selective as possible. Misconfigured GC settings can exacerbate GC issues. Choosing an unsuitable GC algorithm or failing to adjust GC parameters based on workload characteristics can lead to longer pause times, increased memory fragmentation, or inefficient memory utilization. Proper GC tuning is key to avoiding these issues. Tombstones, markers indicating deleted data, are necessary for eventual consistency and data cleanup. However, excessive tombstones can lead to increased memory usage and GC overhead. Efficient management and compaction of tombstones can help keep this issue in check. Last but not least, a high number of tables and key spaces can increase memory consumption and GC pressure. Each table and key space adds overhead to the system. It's important to manage your schema carefully to avoid unnecessary overhead. In summary, GC issues in Apache Cassandra can arise from a variety of sources: heap size, misconfiguration, high write throughput, large partition reads, long compaction tasks, improper data modeling, suboptimal query patterns, misconfigured GC settings, excessive tombstones, and a high number of tables and key spaces. However, with careful management and best practices, these issues can be mitigated, ensuring optimal performance of your Cassandra clusters.